Okay, hello everyone. Welcome to another lecture of the course, and this one is about liquefaction of gases. So this is going to be the first applications lecture after introducing all the formal aspects that we saw in the previous very lengthy lecture on thermodynamic potentials. So now we are going to have occasion to apply all of these tools to a practically useful thing, which is cooling down real gases and eventually liquefying gases. Okay, so we are going to connect directly with the end of the previous lecture. That was the historical experiment that Joule did based on theory by William Thomson, and this was the porous plaque experiment. So we're going to, from that experiment, or from that setup, we're going to define a new thermodynamic coefficient, that is the Joule-Thomson coefficient, and this alpha JT that I have there in the summary, and we're going to discuss the sign of this coefficient, because depending on the sign, for instance, when it's positive, this coefficient, then if you have gas flowing in steady flow conditions and you manage to reduce the pressure of this gas by expanding it, then if alpha is positive, the temperature may go down. Okay, and you might engineer things so that the temperature goes down by a lot, eventually even maybe liquefying your gas. Okay, so in discussing the sign of this coefficient, we will have to establish the sign of the heat capacity at constant pressure. Now we could simply say that from experiments we know that the heat capacity at constant pressure is positive, and that's it. But we can actually prove that it has to be positive because we have enough formal tools to do that. And that's actually quite an interesting part of this chapter. So using arguments of stability and using, say, if you want, invoking the Clausius theorem, or the principle of maximum entropy, if you like, we are going to be able to show that the heat capacity at constant volume is always positive, and that the heat capacity at constant pressure is always larger than the heat capacity at constant volume. Okay, so this is completely general for any thermodynamic system which is stable, in a stable equilibrium state. Okay, so once we have done that, we are going to discuss something that is called the inversion curve. In the PT representation, we're going to see what's the area in which this coefficient, this Joule-Thomson coefficient, is positive for any gas. And here we're going to talk about liquefaction in practice, but okay, this practice is not really very practical, because we are doing theory and we're going to remain very abstract. But at least I'm going to say a few words about how liquefaction is done, how you can set up a liquefaction facility, like, and then we are going to specifically see what the inversion curve looks like in the van der Waals gas, so with the van der Waals equation of state. And just to conclude, in the very end, we are going to, again using the van der Waals equation of state, we are going to write down explicitly the internal energy and the entropy of a van der Waals gas. But actually the way we're going to do it is, well, it's very simple, just direct application of the TDS and the energy equations. But you can, in principle, use any equation of state of any other gas, which is not van der Waals, and you would, again, have a general form for getting the internal energy and the entropy. Okay, so I will start in the next video already.